Hello and welcome. Good afternoon. My name is Christos, and together with Thanos and the rest of the team, we will learn, or at least attempt to learn, GPU programming. And I'm sure many of you 5 years ago would never think you will be in this session talking about GPUs and how to program them, but here we are. So we will discuss about a system we have been developing at the University of Manchester for the last 10 years, which is called TornadoVM. And in this session, we will go through a little bit through the history of TornadoVM, how it started and where it is now. And then we're going to dive down to GPU programming models. So why they are so different and why they are so hard to implement in managed programming languages. Then we're going to switch gears and we're going to discuss about TornadoVM, the architecture of TornadoVM, how to program with TornadoVM with live coding examples. And then after the break, we're going to go deeper into the internals of the system, how it works, how it generates the code, and how it orchestrates the code. And finally, we will close the presentation with the tool sets of TornadoVM and some practical applications with a focus on AI. A few words about us. We are the TornadoVM team, as we call ourselves. I'm Christos. I'm an associate professor at the University of Manchester, and I have been leading this project for the last 10 years. And together with us, we have Thanos, Mary, and Michalis, who are researchers, and they have spent a significant part of their lives, the last 10 years, to develop and optimize TornadoVM. Let's talk a little bit about the history, how it all started. It all started around 2017. So back then at the University of Manchester, we had some questions. We could foresee that GPUs, or at least the need for improving the performance through massive parallelization, which is offered by GPUs, in the future will become very significant. And we had some questions regarding what it takes for a JVM or the Java language itself to enable this capability. And we developed a system which originally it was called Jack, and it was based on the suit framework, which is, let's say, a compiler that was plainly taking Java bytecodes and then it was producing PTX for CUDA. And that first prototype was more about us. It was more about our team to understand how many things we have to break into the JVM in order to make GPU acceleration practical for Java developers. And as we were getting into the answers and publishing papers and doing work, Jack, the original framework, was improving, and it was changing. So it was a big milestone in our development at 2018, where we adopted the Graal compiler, and we open-sourced the project at 2018. And since then, we have 23 releases. Currently, we are 1.1.1. And all these years, although it started as a project for us researchers to understand the problems that Java has and the JVM has, the challenges, how to do GPU acceleration, it incubated throughout the years into a production-ready system. And we have been very lucky because this year was the first production deployment of TornadoVM in the context of the European Space Agency Gaia mission. So a few words about the Gaia mission. The Gaia mission is the most successful European, let's say, space program, where we sent the Gaia spaceship to do a 3D mapping of our Milky Way galaxy. And all the data, all the images coming back from the Gaia spaceship, they were processed at the University of Geneva in order to create data sets for the researchers to perform their physics research. And in this pipeline, in this extremely complicated and really large data processing pipeline of the European Space Agency, TornadoVM managed to intercept, do GPU acceleration, and reduce for a large part of the pipeline from 1 month processing of data to just 5 days, which is a really significant part since this data consequently are being used by physicists across the world to perform and understand our galaxy. We were very happy about it because the way we achieved that, so the way we managed to create a system from a research prototype to a production-ready system was through some decisions we made back in the day, which back then, to be honest, we were not thinking about too much about the productization, but more about the performance. And our transition to the Graph framework and the way we plug into the JVM, it's really unique. It means that TornadoVM is not a replacement of the JVM. TornadoVM is a plugin to existing JVMs. So regardless if you run OpenJDK, GraalVM, Temurin, or Mandrel, you can download your distribution and plug in TornadoVM just like that. And automatically, you have access to a very mature ecosystem of system software and tools that, if you want, you can enable GPU acceleration. The fact that, let's say, we have it there as part of the JVM, it does not mean that you really need to use it. It will stay on the side, and if you like to do GPU acceleration, it's there to provide this performance. And because we are being based on Graal, we also have access to GraalVM polyglot runtime through the Truffle framework, meaning that even if you have code that is JavaScript or Python or R, which actually is being run on GraalVM, and you have some Tornado code that can be offloaded on the GPU, you can call directly this code from any programming languages that GraalVM supports. And this whole concept of having a very versatile system that can plug into OpenJDK distributions or JVM distributions is paired with the fact that we have 3++ backends for TornadoVM. So regardless if you have CUDA or NVIDIA or AMD or GPUs or FPGAs, there's a high chance that TornadoVM can compile dynamically the code and run it on these kind of devices. At the moment, we have 3 mature backends, OpenCL, PTX for CUDA, and SpearV, and now we are developing a Metal backend for Apple. So despite, let's say, the system software that enables this acceleration, we also, because we are just a plugin for Java, we can benefit from the rich ecosystem of Java, from programming to deployment to debugging. So everything is Dockerized, can run on Kubernetes clusters, and we have implemented many tools that can help developers do the first, let's say, baby steps into the new world of GPU programming. It's a bit of a different, a strange world compared to what we Java developers are used to, and we need tools to help us understand it and optimize our code for that. And of course, naturally, the last couple of years with LLMs and AI, we switched gears, and now we are optimizing TornadoVM to do native GPU acceleration of AI application. And we came a long way, and now we can run AI workloads, production-ready, natively written in Java, and compiled and run on GPUs. So on the right-hand side here, we can see our inference engine running on TornadoVM, which does inference on a Llama 3.2 model. And on the bottom part, we can see in the blue line the spike on the GPUs. Imagine you have your laptop, and then you code this application, or you download our implementation, and as soon as you fire this application, you can see that the JVM calls Tornado and offloads execution on the GPU. And this has 0 third-party libraries. This is all pure Java. We write Java, and the system compiles the code, runs on the GPU, and because of this, it allows us to do integrations with LangChain4j, Quarkus, Spring Boot, and all these modern frameworks to enable and augment the existing Java ecosystem regarding acceleration. I will not go very much into this. There is a special talk by Michalis on Thursday regarding GPU Llama 3 and how to run native Java inference on GPUs, which will go into much detail. Let's take a step back and go to the basics and ask the question, why do we need a system like TornadoVM? The reason we need it is because we cannot program GPUs with a current JVM. Why? Because GPU programming is very different. And to answer how much different it is, I will pass the mic to Thanos, who will take over and discuss about the programming models.
Thank you, Christos. So yes, how much different is GPU programming from programming in Java? Well, the answer is already given by Christos. It's very different. And the reality is that as Java programmers, we have used to different way of thinking and programming. So mainly we can exploit parallelism through available APIs like the vector API or coding with parallel streams or recently with the virtual threads. But this, in fact, it has been used in order to exploit parallelism at the CPU level, so when we are running on the CPU. But the reality is that in modern hardware, we have available more power given by exotic hardware resources like the GPUs and even FPGAs or other accelerators. So in order to harness them, we need to start thinking differently with a different mindset. So when we want to exploit, for example, a GPU that has multiple CUDA cores inside, for example, for NVIDIA GPUs, we may start thinking that we need to express the computation at the thread level. And because we need to start thinking at the core, one core, what we would like to run. And then the same computation is running by different threads or different data. And there is where we can actually get performance. And we need to start thinking as well about the hardware a little bit. So how all these threads are grouped. Because we can see here that they have a cache. So they have the local memory, what we call, in OpenCL. And in order to get performance and ensure fast memory accesses, we need to start thinking how the threads will be deployed. So that's why we have a small session where we will introduce the GPU programming models to whoever don't have a clue. The reality is that we have all this hardware coming up, GPUs and FPGAs as coprocessors to the main CPUs. And the idea is that the ideal scenario is that we want to offload execution from the CPU on these accelerators to perform fast, reduce the energy consumption, and improve our performance of our applications. So as developers, as programmers, we get new hardware. We're very excited to use it and get performance. But the reality is that we're facing some questions that they may be mapped into actual challenges. For example, we get a GPU card. We say, OK, which driver do I need to install? If I want to program and offload execution on the GPU card, then what SDK do I need to install? And essentially, how do I offload the execution on these cards? And all these questions, they are associated with what we call a programming model. So in a sense, programming model, it is an abstraction. It is a set of rules and principles that the programmer needs to adhere to in order to be able to perform actual computations on the GPU cards. And this is an abstract view of a programming model. So there are many available programming models, and they may look like this. So there is an SDK at the top that exposes an API to programmers. So programmers can include the headers. They can actually use these API calls to perform some specific steps that we will follow in a bit. And then there's the runtime, where we have the libraries and daemons, and they are available on the system to intercept the API calls and translate them into actual operations that will be performed by the drivers. And there at the runtime, we have the execution model. We will visit it a little bit later. And we have also a memory model. As we said, we have the DDR, which is the global memory on the GPU, but we have also local caches memories for faster accesses. So we need to start thinking about how we will exploit the memory as well. And finally, we have a compiler, which usually it is inside the driver and performs the final code generation. So it takes a code format from, for example, a source code like OpenCL, and generates the final binary that will be executed on the GPU cores. And here are some state-of-the-art GPU programming models: NVIDIA CUDA, OpenCL, and SPIR-V and OneAPI. OK, we have discussed a little bit about the abstract view of what is a programming model and what it has inside. But here is a landscape of the available programming models that are available in the market. So as we see here, there's the SDK on the top. It exposes the API in different proprietary or non-proprietary programming models. We have the compiler, which is mainly LLVM based and performs all this optimization of the code to run in parallel. And finally, we have the generated code, which is the final format before going to the binary. So as we see here, DBC++ can generate SPIR-V and Vulkan. OpenCL supports OpenCL and SPIR-V binaries, etc. And we have more information in the book that we have written, and in particular in chapter 3, where we actually give an overview of programming models. And in fact, all the examples that I will show you in the next slides are part of the book, so you can follow them one by one. OK, so we're programmers. We have a program in C++, let's say. And we can start thinking differently. So we need to think that we have the host code. It is part of our application, where we will actually invoke the kernel to be executed. And then we have the actual kernel, which in a sense it is a C++ function that has been expressed differently in order to run in parallel. And the first step that we need to do is to explicitly create some data structures. So these data structures are programming model specific. For example, we have the context, which is a data structure that enables the communication with the driver. Then we have command queues, or CUDA streams, as they're called in CUDA. And if we have a look, this is a command queue. We are programmers. We're at the SDK level. We use the API. And we enqueue commands in the command queue. So in a sense, we enqueue all these operations that we want to explicitly define and declare. And then the driver is responsible to fetch these commands and actually execute them. And this is the way that we will start thinking in the next slides. So for example, the next one is the actual creation of some internal buffers where we want to map the data that we have in our application. And to do that, we will use these API calls. We will create the context in order to get the context data structure. And then once we have created the context, we will pass it to create a command queue. OK, so let's start thinking with an example. We have a kernel, let's say matrix multiplication. We have two input matrices, A and B, and one output matrix, which is C. And in order to create some data to offload matrix A, B on the GPU memory and do the processing, we need first to create the data buffers explicitly. So we're using the CL create buffer with the OpenCL programming model. Then we are creating a second buffer for matrix B and a third buffer for matrix C. And once we have done this, we can see that this call returns back a pointer. This pointer, it points to the device address space. So it points to the actual addresses that we can see in the GPU memory, in the DDR inside our GPU. Then, in order to access these pointers, we need to map them into the host address space of our program. And to do that, we are using these calls, the CL-enqueue map buffer, where we actually map, if we see here, I don't know if the laser is pointing correctly, but we have the DA, the second parameters, DA, DB, and DC. In a sense, it is the device pointers. And then we are passing, we are returning back the A, B, and C, which are the actual pointers into the virtual address space of our program. OK, we have created the buffers, and then we're moving into the actual transferring of the input data. So we want to transfer A and B data into the GPU memory. To do that, we explicitly call the CL-enqueue write buffer. The first argument is the command queue, where we will issue this command. Then we pass the device pointer, and then we add also the host pointers there. So we need to explicitly write the buffers. And once we have done this, then we move to the next step, which is the actual definition of the kernel. So now we did all this part previously. We were on the host side. And now we need to move into the kernel side. So we have matrix multiplication. And we need to start thinking a little bit different, as I said, for GPU programming. So we need to use some classifiers in OpenCL. We need to define that this function will be a kernel in order to be identified for GPU execution. So we're using this keyword. Then we define the return type, which is void for OpenCL and CUDA. Then we have the kernel name that we will use later in order to compile this kernel. And finally, we have the arguments. So these are all the arguments of this function. We have matrix A, B, which are inputs, C, which will be the output, where we will read the data from. And then we have some sizes for each dimension of the matrix, let's say. But what is important is that we have also the kernel body. And this is where we actually express the parallelism, express this kind of a computation that we want to run. OK. And we have the grid. So now we need to start thinking as GPU programmers. So we need to be aware of the hardware, how it is placed. And the OpenCL and CUDA, they expose a grid, what we call. It is a three-dimensional cube where you can actually see that each one cell, it is a GPU core. So if you want to offload a 3D matrix, you can utilize a 3D dimension grid. And that means that it will run, each computation by each thread will run concurrently. So what we see here, it is the cube. Each cell, it is a work item. But we have then also the orange cube, which is part of the main cube. And this defines the work groups. So this is a group of threads that they can access the same local memory. So if you want to exploit local memory and improve the memory accesses, you can also start thinking how I will group the data. And this is something that GPU programmers are very good at in order to tune the performance of their accelerated function. So here, as we see in this example, we are getting the global ID of the first dimension, 0. We are getting the J, which is the identifier of the second dimension. And then we actually have this purple surface where we actually will map all these threads to run our data. Because in our example, we have a 2D matrices. So we're doing a 2D matrix multiplication. OK, I hope you are not very intimidated by the previous slide. So now we are ready to actually create some more data structures for the kernels and to actually set the arguments before we actually launch. So as we see here, we need to create a program. We pass as input the source, which is a source file. So as we will see later, we have a source file where we have the kernel expressed inside. Once we have created the program, we actually build it. And then we are ready to create the kernel in order to start the execution. And inside the CL create kernel, we put also the name of the kernel that we have defined and we want to run. And the next step is to actually define the arguments. So as we will repeat here, we have the kernel signature, and we need to, in the first 3 arguments, we have the device pointers, so the pointers into the GPU memory. And then we map each one of them into the actual argument of the kernel function. And then we are ready to launch the execution of the kernel. So we need to start to define also the grid. But before we define the grid, we have the CLNQ and the range command, where we pass the command queue. We define the dimensions of the matrices that we will launch. And one of the parameters is the kernel event. And this object is used in order to identify for this command a specific event. This is very useful if we want to wait a command, to wait until a previous command has been completed. So sometimes we use it in order to profile the data transfers. So we say that we want to have a look how will be the elapsed time for transferring the input data. And this is done through the events, by utilizing the events. And the next step is to manually define the grid. As we see here, we have 2 dimensions, 0 and 1. We need to think about the grid. So as well, we define the local workgroup size in order to improve that. And if we have this example of 8 by 8 elements, which is very small, but just for the sake of this example, then we will define a grid to cover all the data are processed. And then we will define as well with the purple box the local workgroup. So we'll have 4 work groups for the execution. And the final step is the definition of the output data. So we will run the matrix multiplication on the GPU. We need to get the data back. And to do that, we need to explicitly read the data. And this is done by this operation, this command. Again, we pass the device pointer where we will read the data, and we pass as well the host pointer where we will have available the data once we return back to our program. And the final step is to compile and execute. So in this example that we have in the link, we have the main program, which is a host C++, a C++ file. Then we have the accelerated code, which is expressed in a second file, the kernel CL. And in order to compile and build it for Linux, you would have to run this command. For macOS, it's slightly different to link with the OpenCL framework. And then you can run. In this case, the first argument is 0, which corresponds to the actual platform. And the second is the actual element size, so the dimension for a matrix, for a square matrix. And if we run, it would look like that. So I think we are ready to move on the terminal. I can actually show you. So this is the directory where we have cloned the repository from the book example. OK, sorry. Yes. Perfect. OK, yes. So this is the directory where we have cloned the code example. We have the matrix multiplication for OpenCL. And here we can have a look. So we see here that we have the host C++ file that I mentioned you earlier, and the kernel CL file. And if I open the CLion, we will see that this is the kernel function that we defined. And we have also this host C++ that has all the code snippets that I showed you in the previous slides. So as we can see here, we need to explicitly do everything, to create the data structures for the model to be able to communicate with the driver, to create the data structures for the input data, to explicitly perform the 3 main steps for executing, which is copy the data on the GPU memory, then execute, and then get the final result back. And this takes nearly, well, we have 413 lines of a C++ program to run matrix multiplication. Well, it is kind of verbose, as you can see. And once we have done this, I think we are ready to move, to the key remarks that we have. So I hope I didn't intimidate you with GPU programming, although this was kind of my objective. So let's have a look. First, the GPU programming requires some different mindset from what we have used as Java programmers. So programmers need to start thinking differently and at the thread level to express the computation. And as I showed you now in the editor, we can have a lot of verbosity, so developers need to do everything explicitly. So essentially, it breaks the promise of Java. So write once, run anywhere. Well, this is kind of difficult for GPUs, let's say. And now I will point to Christos, who will take over in order to introduce you how TornadoVM solves this problem.
Thank you, Thano. So as Thano showed here, when we started the development, we realized that for just a simple matrix multiply, which is a very common process, or at least a function we do in Java, we really require 400 plus lines of code in OpenCL or CUDA, if we write CUDA. And from this realization, like how to create a bridge or a system that will help, let's say, Java developers to create and develop GPU applications, many of our decisions and our thoughts were always this trade-off, performance and programmability. And to solve this trade-off, we designed the system, or at least we morphed the system through the years in order to give the power that OpenCL or CUDA gives, but by maintaining all the Java goodies like abstraction and platform portability and being platform agnostic and optimize the code transparently to developers. And to do that, we designed the system in a way that it hides all these, at least the majority of these 400 lines of complexity under the hood, so developers can just use TornadoVM to express just the computation, and then TornadoVM handles everything underneath. And we had to leverage, or at least to satisfy two parts of the execution. First is to be compatible with the Java ecosystem, and on the other hand, we have also to be compatible with all the drivers and all the platforms and all the devices that might exist. Now, when a new architecture comes, for example, RISC-V, we don't worry about our code, our source code, because this is a job by the compiler engineers to write the assembly for RISC-V and make the JVM compatible with RISC-V. The same ideas we want to apply for acceleration on GPUs and FPGAs. That's why TornadoVM has been designed in a way that regardless if we have GPUs or CPUs or FPGAs, they're going to compile and optimize the code for the device. And even better, it has also the capability, if you have a full heterogeneous system with 10 GPUs and 10 FPGAs, it will dynamically find for you the best mapping of code hardware to give you the best performance. And this is achieved by a system which, if we zoom out and we have an eagle eye view of the system, it comprises 4 building blocks. It is what the developer see, the developer API, and the whole Tornado runtime, which is hidden by the developer. And in this presentation, essentially, we will examine each block and what each block does for the system and how it's being used. At the top level, we have the API, which is the only thing that developers see, like how to program, how to write a code that can be GPU compatible, and how to orchestrate, let's say, the execution between the different devices. And as soon as the developer performs these tasks, the next step is Tornado handles over all the heavy duty. It will optimize the graph, it will create data flow graphs, it will optimize them, it will create orchestration bytecodes, it will call the execution engine to start executing the code on the GPU or any accelerator. And when it's time to actually, like a split millisecond before we send the code to run on the GPU, this is where the compilation, the final compilation takes place. This is, we call lazy compilation. And at this point, we call our compiler, which is an extension superset of the GAC compiler that will take the Java bytecodes and it's going to produce OpenCL or PTX for CUDA or SPIR-V or Metal, whatever we want to, whatever we define to run. And by having this modular architecture, it allows us to be very fast and very reactive to new platforms, new engines that come into place if we want to plug in a new backend for execution, or if we want to apply optimizations, which in our case, that was manifest by the arrival of LLMs. So although in the beginning we are writing general purpose programs for GPU acceleration, the switch to AI and LLMs now has created a use case for us where the modularity of the system allows us to go into different layers, the graph level, at the assembly level, and then optimize and get good results through native GPU acceleration. And although developers don't need to worry about all these layers because they're just users of the API, the open source nature of TornadoVM and the fact that anybody can come to our GitHub page and open a pull request for some optimizations for the specific workloads allows us to create a breadth or at least a big capability to optimize on the same platform for different use cases, regardless if they are AI or just pure Java analytics that many people use. So from this point on, I will pass the microphone again back to Thanos, where enough with slides, and now we're going to go into more practical examples and enjoy.
Yes, so let's move to the actual setup of Tornado. So I have a MacBook M4 here, and now we'll switch to the terminal. So we have cloned the repository. Let's move the tab. Yes, we are in TornadoVM. So as we see here, yes, we are in the Devox 2025 API demos branch, where we have some examples that we have shared as well, some leaflets with you. And as we see here, we can leverage the TornadoVM installer that we have in in the TornadoVM repository. So here it has recognized that we have a Java home. If we didn't have the Java home, it will ask the user to actually configure which one of the available JDKs that Christos showed earlier they want to use, and would automatically download it in order to have it. And then it has detected the Maven distribution, and has also detected the CMake. So these three are the essential dependencies that we need to have in order to actually run TornadoVM. And then the user needs to select a backend. So right now in the MacBook 4, M4, it supports only OpenCL, so we need to install only with OpenCL. And then it triggers the actual build, and will build all the modules that we have inside the TornadoVM. The API, the examples, the test suites, everything. And once it has done this, then we are ready to run, let's say, the TornadoVM programs, in a sense. You can try the Tornado unit test. You can try the Tornado examples that we have in the repository. OK, it has done this. So we need to source a set path that has all the Java home and the Tornado SDK path. So in fact, we can have a look in the set vars. So we can see here, it has the Java home, it has a path for the binaries, and then the Tornado SDK. And we can actually perform and run Tornado devices, which will actually query and see how many availables there are available on this computer. OK, we have done this. And now we can show you as well that you can also initialize IntelliJ init. You can run IntelliJ init. It will create some XML files, and then you can move to the actual IntelliJ, where you can see here at the top that you have some files generated, especially TornadoVM build, TornadoVM tests, and the internal. And you need to install the plugin for Python. And once you have done this, you can actually configure the Python XML files. So you need to set up the Python SDK here that you want to run. And if you click apply, let's see the test as well. Yeah, the same. If you click apply and you run, then you actually build on the IntelliJ, inside the IntelliJ. And this is where we actually can build TornadoVM on the IntelliJ. We can add breakpoints, and you can actually debug any programs or applications that we have. OK, we have, it moves on the building on the IntelliJ. So I think we are ready to pass to Mary, who will give you an introduction to the API level, let's say, of TornadoVM. And we will actually go into more practical examples. Let me go back to the slides. OK, yes, sorry. So here is the slide where we have actually the repository, so the link to the repository and all the information how to run and initialize the IntelliJ.
Hello, everyone. My name is Mary. And in the next few slides, we will describe with Thanos the highest level of the TornadoVM software stack, which is the APIs that you can use in order to develop your application to be executed on the GPU with TornadoVM. So TornadoVM essentially follows the same computational model that OpenCL and other low-level programming languages use, which is to have an accelerated method, the method that will be executed actually on the GPU, and the host code, which is responsible for the dispatching of the code and the data, and the actual launch of the application. So let's start, firstly, with the way that you can express your function to be executed on the GPU. And let's actually have a look at some code again. So I think at this point, it's become pretty evident that developing code for GPUs is a very hard task. You can see that even for this matrix multiplication example, you need to be aware of the different memory regions. For example, for the global here, you need to be aware of all the different IDs that you need to use. Now we'll show you how you can express the exact same computation in Java using TornadoVM. So here you can see the matrix multiplication example, which is written purely in Java. So this looks very close to something a Java developer would write. You could say that there are two for loops, which are iterating over the data of the matrices in order to perform the actual multiplication. And because it's a Java program and it's configured also on the IntelliJ, I can simply run it from here. You can see it's being executed on the OpenCL device, and we get 59x speedup for it. So now let's explain a bit in more detail the programming flow of TornadoVM. So there are two actually key components of the TornadoVM programming model. The first is about expressing the parallelism of the computation so that it can be executed optimally on the hardware device that you use, the GPU. And the second is regarding the data types that you will use in order to express the data for your program. Regarding the expression of the parallelism, TornadoVM offers two APIs, two different ways to do this. The first is the loop parallel API, which is more suitable for developers who have never programmed in GPUs before, so essentially the average Java developer. And the second is the kernel API, which is more suitable for developers who have some experience in low-level programming because it gives them access to low-level control features of their application. Let's move again back to the code now. You already got a sense of the loop parallel API here. So as you can see, this implementation uses these at parallel annotations. And what this annotation does is that it indicates that there are no data dependencies in the loops that are annotated. So for this syntax, you can run independently for the data structures that you are accessing. Then, if you include this at parallel annotation in your code, the TornadoVM compiler will identify it and perform an analysis to ensure that, in fact, this is the case and there are no data dependencies. So even if you accidentally put it in your code and there was dependency, you don't need to worry about it because the TornadoVM will take under the hood, take care of everything. Apart from this at parallel annotation, the loop API also exposes this at reduce to take into account the different special case, let's say, of parallelization. So here you can see an example of a reduction. We have an input array, and we accumulate all of its elements into an array called results. Here you can see that we also again use that parallel annotation because we iterate the inputs with I independently in its iteration. And because here in the results we store the results of the reduction, we include here in the argument list the @reduce. And that's it for the loop API. So you just utilize either of these two annotations, and TornadoVM takes care of all the thread synchronization, all the parallelism, everything. But as we said, there is also another API, the kernel API. And here you can see the same matrix multiplication written with it. As you can see, this is very close to the OpenCL code that Thanos showed before. And we also saw before. So you see that there are the global thread IDs, but now we get them from this kernel context object. So what this is, essentially it's a class that exposes some low-level details, like the global thread IDs. We have the local thread IDs. We have the different group sizes per region of memory. But it also enables developers to have more control of the flow of the program. So they can include barriers in local memory or global memory. They can allocate arrays in local memory of different types. Here, as you can see, we have int arrays, long. We have float arrays, double, and you can even perform atomic operations. So I will show you now another example of matrix multiplication, a very optimized implementation, which takes advantage of the capabilities of the kernel API. So in this implementation, you can say that it uses some optimizations, like it allocates in local memory. It uses styling, and this is a very, very, very fast implementation of matrix multiplication. Writing this code would not have been possible with the Loop API. So in a sense, the kernel API is complementary to it. OK, so now that we have discussed about the parallelism, let's talk about the types that TornadoVM supports. The types that TornadoVM supports essentially can be split into two categories. There are the on-heap types, which are essentially the Java primitive arrays, like int array, float, and so on. And then we also provide our own types, which are off-heap, and are implemented by taking advantage of Project Panama. Now, I'm sure the majority of you is familiar with Project Panama, but because later on we will show how we actually utilize it, I have a couple of slides which explain some basics of it. So Project Panama essentially acts as a bridge between JVMs and native libraries. And some of its key features include the foreign function API, which enables developers to invoke native code from their Java applications, and the foreign memory access API, which enables developers to access and manage memory off-heap. And this is what we actually take advantage of for types. The key elements of the foreign memory API that we utilize in our code are the memory segments, which represent a bounded continuous region of memory, the memory layout, which defines the type of the data stored in the memory segments so that we know how to access it, and the arena, which is responsible for managing the life cycle of the memory segment, the allocation and the allocation. OK, so let's look now at the types and how we actually take advantage of all this functionality. So TornadoVM, in fact, offers many types, depending on your application. For example, here, if you can see the packages, we have arrays, native arrays, which semantically, they're one-to-one mapping with the primitive arrays that we support. We have collections. We have matrices. We have many different types. But for the sake of this demo, let's go through the simplest form. All of them internally utilize Project Panama in a similar manner. But let's look at the float array, which we also saw in the matrix multiplication. So here you can see the constructor of the type. As you can see, the developer just passes the number of floats that they want to allocate. And then internally, the constructor calculates all the bytes and uses the arena to actually allocate the memory. You might notice here that we also save some space for some header bytes. This is to essentially store the size, the number of float elements in the float array for some metadata for the compiler. And apart from this constructor here, we offer several different ways for which you can initialize the data. You can concatenate different float arrays, for instance, into one. And here you see again that we just use the memory segment internally, so it's nothing fancy. We can take a float array from on-heap and then convert it to off-heap. We can even take elements, like Java offers this option, individual elements, and then store them in the memory segment. And we can also initialize from segment. So if you already have an application that takes advantage of Project Panama, you can simply pass your segment and create this type. And also, there is the float buffer option. And we also have some functions, some setters, some getters to access this data. So here you can see a set where we simply invoke the function from the memory segment, and we define the layout of the data so that we know how to access it. We have some helper functions like the clear, which initializes all the value of the segment to 0, or you can invoke the init to initialize it with a specific value. We have some functions which you can use to get some general information about your data, like the number, the size of the type that you have. So here it's 4 bytes for the float, the number of elements that you have, the number of bytes with or without the header, which might be useful to know for an application. And then you can access the data in different formats again. You can convert it back to a float array on heap. You can get the segment with or without the header bytes. And you can get any random slice you wish to utilize. Sorry. So I know at this point you might be thinking, oh, so now we have to learn all these new types in order to take advantage of TornadoVM. Because we are also developers and we know the pain that you have in order to learn new data types and new APIs, we try to make them as easy and seamless to integrate as possible. For example, as we showed before, if you have already an application that uses primitive arrays, you can just pass the array to the constructor. We have this from elements that I showed you before, which is very close to something a developer would write, because as you can see, this is very close to Java's way to initialize from elements. And importantly, because the adoption of Project Panama is going to keep growing, we offer this way to actually pass your segment, which is it's going to be very useful in the future. So we believe that in this way, the gain is larger than the pain. So now we have gone through the key concepts of programming, and I will pass to Thanos, who will show you how you can actually dispatch this code.
Great, thank you, Mary. So yeah, we have seen the way how to express parallelism inside the method. So we have created a parallel computation, we have expressed it. So now we will see how we can dispatch the kernels and actually invoke them from our Java applications. So we need to reflect back on the development flow. So this is the step one, what Mary showed you. It was part of the actual accelerated code. Now we're moving into the host code parts. So in a sense, we have the second step, which is how to dispatch code and data, how to define which data to be moved, where to be moved, and which code to run on the accelerated card. And then the last step, it is how to launch execution on the actual accelerator, so how we invoke the actual execution. And we have some objects in the TornadoVM API, like the task graph and the Tornado execution plan, that they actually run everything, all these steps. They enable programmers to express them. So if we reflect back to the execution model that we briefly described previously, so thinking with according to the GPU programming models, we have the first step to be the transferring of input data to the GPU memory. The second step to be the actual execution on the accelerated card. And the third step to be the retrieval of the actual outcome back to the host memory, to the CPU memory. So if we think this analogy in the Java world, it would mean that if we are using primitive arrays, it would be from on heap to do the actual moving to the GPU memory, to the GPU DDR, then do the actual processing, and then copy the data back to the on heap memory of our data structures, our objects. So we are moving into the dispatching of the code and the data. We need to consider that we have a method, let's say method A, and this would correspond to what we call in the TornadoVM terminology a task, so task A. And similarly, we can express multiple tasks that we want to run on the GPUs. So we can have a method B, which corresponds to task B. And if this kind of tasks, they have some relationship, we can also chain them together to create and compose task graphs. So in a sense, consider that you may have a method A, that creates a result that method B will consume, and you don't need this result anymore. So ideally, what the task graph would do, it would be to run first task A, persist the data in the GPU memory, so don't copy back to the Java world, because they will be used by task B, and then perform task B, run it, and then get the final result back. So that could be an ideal scenario where TornadoVM API actually performs this kind of optimization to improve the data movements. But here we have an example. So we need to define a task graph, as we see here in this API. We pass the actual name, so it is a string, TG in this case. And then we have all these API methods that are exposed through the task graph object. And if we do the analogy to this execution model, we can see that the first method corresponds to the actual transfer to device, where we can define the actual mode that we want to be sending the data. So it can be during the first execution if you have read-only data. It can be during every execution. So, and we pass as well the arguments of the inputs. So in this case, we have method A and method B that have inputs. So we want to pass both of them, input A and input B. Then we move to the actual definition of what we want to process. So we are using the task method to define a task. We are using a string as a first argument, method A or method B, in order to be able to identify which method we want to run. We will see later that it is very useful, especially if we want to do performance analysis, to see the metrics of each task, to know the execution time of each task in order to optimize. And we pass, we have a second argument, the actual method reference, which will be used to do the JIT compilation into the GPU code. And the rest are the actual arguments of the methods. So input A, input B, and any other field that they may have as input. And the final step is the actual definition of which data will be the results that we want to copy back. In this case, we see that we have output A and output B, and we want to send them back during every execution. So after every execution, to send back the data. Once we have defined a task graph, this is a data structure that can be modified during the programming time. But once we have defined that and we are ready to deploy on the GPU, we are very confident that this shape of the task graph will be ready. Then we will create a snapshot, which will generate an immutable task graph. So this object, it is locked at this stage. It is ready to be JIT compiled, so it doesn't allow the programmers to do any modifications at the API level. And this is very useful because you may consider a program that you want, when you write it, to change behavior. So you want to change the data. You may want to to add a new task in it. You may want to save. So in this case, you don't need to rebuild your program and run it. You can just create your program, the whole shape of task graphs, different variations. And with immutable task graphs, you have this kind of opportunity to launch everything with one build. OK, we have created a mutable task graph. And now it is the time to express how we want to run. So we will actually declare a Tornado execution plan. We will create it. And we will pass as argument one immutable task graph or many immutable task graphs if we have, for example. And as we see here, the execution plan exposes one method, which is called execute. OK, we have seen this is kind of complete example of the API and how to use it. So let's have a look into an actual example of the matrix multiplication. As we see here, it is a code snippet of the main method. We define the data of the matrices. We randomly initialize them, matrix A and matrix B. And then we actually do the invocation of matrix multiplication as it would be in Java. So it will run sequentially on CPU. So if we want to translate this into a TornadoVM equivalent implementation, we would do something like this. We would create a task graph. We would leverage all the API methods. Remember, transfer to device to define which data to send to the GPU memory as inputs. Then define the task. In this case, it will be the matrix multiplication method of the matrix multiplication class. And we have also the arguments, matrix A, matrix B, matrix C, and the size. And the final step is the definition of which data to read back in order to get all the results back from the GPU memory to the Java world. We define the immutable task graph, so we create a snapshot, and we actually create a Tornado execution plan. The execution plan has this kind of configurable way for the programmer, so you can use the with batch if you want to batch your data into smaller chunks to execute them. So this is the batch processing that we enable in the TornadoVM API. You can actually define a particular device that you want to run. You can define that you want to run with a profiler for the first execution. Then the second execution in the code, you may configure it to run without the profiler anymore, so that you can see the results of the first time and then to see how it will affect profiling the final performance. You can run with a specific grid scheduler and with profiler. Yeah. So this is how to run. And as we see here, if we were using the kernel API for expressing the parallelism inside the method level, as Mary showed you earlier with local memory for the optimized version, we would need also to manually define the grid, similarly to what GPU programmers would do. So in this case, we create a worker grid, as it is called, this object, and we pass in the constructor the size, and this corresponds actually to the dimensions that we want to deploy on the GPUs. And as we see here, we have the global size, which is defined by the constructor. It will be size by size. But we have also the ability to set the local workgroup size. So how we want to group the threads to be deployed in order to access the data from the local memory. And this is very important because programmers can tune it, so they can see how it affects the performance, the actual deployment of their applications. OK, and if we have a matrix size by size, this would be the worker group. And then once we have defined the worker group, we need to create a grid scheduler. So this is where we map the actual name of the task that uses the kernel API, and we associate it with a worker grid. So that means that TornadoVM will launch this task with a worker grid that developer has defined. And once we have done this, we can actually start the execution. So this is where we actually leverage the execute method of the TornadoVM execution plan. And this will do everything, pretty much. It will transfer the data. It will decompile the code. It will send the data back. So it will do everything, pretty much. And now I think it's time to move to Intel again. OK, we have the matrix multiplication. Let me close the Tornado inside. It's too early for that. OK. Yes, so this is the code that Mary showed you earlier. As we see here, we have the class matrix multiplication 1D. We have defined the warm-up iterations. So in a sense, we want to run multiple times, in this case, 15 times, the actual kernel on the GPU. So it will run 15 times. We have expressed the parallelism at the task level in a method. So we have created that. And we have, OK, initialized the data. That's obvious. And we are creating the task graph. So this is what I showed you in the code snippet earlier. We have an immutable task graph. We define the execution plan. And in this case, we configure the execution plan to run with pre-compilation. That means that JIT compilation would be performed once. The code will be already JITted at this point, in this line, and will be stored in the code cache. So the OpenCL kernel will be already JIT compiled the first time at this level. And when we are doing the iterations to execute the kernel, the code will be already JIT compiled, so we will not have the overhead, let's say, of the GraalVM compiler to compile it. The TornadoVM, essentially, compiler. So we run 15 times, yes. And then we have a final run, let's say, the 16th time, which will be the final execution. And then we have the sequential. OK, let's run it. So this is what we see in the console, multiple executions, 15, and then we have the final execution that we see here in M4. OK, and I have created, because I like breaking things, I have created a different variation of this program. So as we see here, we'll see the differences in the actual code. So what we see here is that we have introduced a second method called spoil results. In a sense, this takes as input a result array and iterates in parallel, so it will assign 0 into actual in every element that we have in the float array. So in a sense, it will spoil the matrix results. But what is the magic here and the powerful of the API that I want to show you is that we have defined, we haven't changed this. So we have the execution plan that will use the task graph that has only one method, the matrix multiplication. We will execute it 15 times. OK, in the meantime, I think it's a good time to build it in order to save some time. Yes, so we are running 15 times, just matrix multiplication. We will get the data back. We will print the actual data that we see here, the matrix C. So we will see the actual matrix multiplication results. And then we change the task graph. So we say remember, task graph is it is mutable. We can change it. So we add a new task, which will be T1 of the same task graph. In this case, we add the method reference for spoiler results, which uses that parallel notation. And we pass the result of the matrix multiplication of the first task. So what it will do, it is, in a sense, reset everything into zeros. We create a new snapshot in order to differentiate from the previous one. And we create a Tornado execution plan. And we pass the immutable task graph 2, which is the new one. And then we actually run. So now, if it is, yes, it is built. So now if I run, we will see that we will run multiple times, so 15 times, and the 16th time will be the actual that has spoiled the results. So as we see here, OK, let me go slightly up to see the threads. So yes, here we see that we have multiple iterations of S0, T0, which is the first task running, one after the other, multiple times. It creates correct results for the matrix. And then once we have printed the result of the matrix for 512 elements, we will be ready to see the final deployment, which has both tasks. It has task S0, T0, which does the matrix multiplication. And then it has task S0, T1, which actually spoils the results. And then we see the actual grids of each task, 512 by 512. And we see that this one, it is one-dimensional, so it has done the multiplication for the deployment of the threads, so it will deploy in one dimension. And all the results are 0. So I hope at this stage I have convinced you regarding the spoiling of the results and how the verification failed. So yeah, I think at this stage we're ready to go back. I think we have time before the break, so we can ask if you have some questions at this stage regarding the API or whatever we have presented so far. Oh, yes. Yeah. Before we go to the break, actually, we have Tornado inside. I forgot it. Thank you, Christos. Yes, correct. So we are in the IntelliJ. I think previously we kind of spoiled it because we had it already open. What we have created, it is a plugin into the IntelliJ for programmers to use to learn how to use the TornadoVM API. And if we go here into the IntelliJ settings, and if we go to the plugins, you can actually search for Tornado inside, because I have already installed it. You can install it, and what will happen it is that it will appear here on the right side, and you will be able to actually configure the settings. So if we go into the panel, we will see that we have this kind of configuration window where you will define at first TornadoVM root. It is the directory where you clone TornadoVM in your system. Then you define the Java SDK. In this case, we will use GraalVM because we installed it with GraalVM, JDK21. Then you can use the bytecode visualizer that Michalis will speak later about this tool. So at this stage, I will not enable it. And then for the dynamic inspection, you need to set and indicate a size of the array size. So in a sense, this is just used by the plugin in order to be able to generate parallel code. It will not run on the GPU. It's just for compilation. And if you are using the Tensor API that we didn't show you today, but we have all the information available in the website, you can actually define here the dimensions of your tensors. And finally, some configurations for debugging for us, for the developers of the plugin, and whoever wants to contribute, because this is an open source project as well. So once we have done this, we can click Apply. We can click OK. And we can refresh. So we see here on the right side the detected tasks, the detected TornadoVM tasks of this class. And as we see here, we have matrix multiplication, we have spoil results, which resets the data. And if we run dynamic inspection, this will trigger the JIT compilation of the task that we have defined in this class. And if it is successful, it will actually throw here the parallel code that has been generated by TornadoVM. So we get also a window that says the inspection time and that it has been completed without an error. But in a sense, here in this Tornado Insight console, we can see any errors that may appear during the code generation that can indicate to programmers that you may have a bug, or you may start thinking slightly different, or something is not supported right now in the TornadoVM side, and then you should open an issue to us to extend our compiler. And yeah, as we see here during the matrix multiplication, we configured with 512, and we will create this kind of parallel code. It has some FMAs. We will go into the code generation in the advanced sessions of TornadoVM. And if we click also for spoiler results, we will also create this parallel code for spoiling results, which, as we see here, we just iterate over the number of elements. And we actually assign 0 into the right address space of the arrays. OK. We saw how it works with dynamic inspection, which actually triggers JIT compilation. But in fact, the Tornado Insight tool has been used also for programmers to help them coding. So we have some examples of what it is not supported in the API level. So let me close some classes. So yeah, if we move here, we have an example where we're actually defining we're trying to express parallelism within a method, the ArrayListAdd, and the arguments are of type ArrayList integers. So this is a dynamic data structure. That means that our compiler, during the compilation time, does not know the actual size of this data structure. So this is not supported in TornadoVM dynamic size. And if we see here, it is marked as red from the plugin, and we get this kind of message that TornadoVM unsupported data type in TornadoVM. And if we do refresh here, we do not see this task as identified in the right window of Tornado Insight. OK, second example that we have is one that throws exception. So as we see here, it is identified because I have commented out the throws exception part of the method. But if I return it back, then it is marked as red. So this is not supported in TornadoVM. In a sense, it is not supported because GPU compilers, they do not support exception. What we could do, essentially, it would be to go at the compiler level and manually remove all these graphs or all these nodes associated with the throwing of exceptions. But again, this is something that we will show you later about the GraalIR and the nodes. The most important part right now is that it is not supported. And then we have the dynamic array. So here, as we see here, it is valid. It is recognized. But in a sense, what it will do, it is that we have one add method. We define internally the creation of an object. So it is a primitive array, D. And then we have we define a for loop where we actually create a new array every time in every iteration. So consider that this is supposed to run in parallel, which means that each GPU thread would allocate a different array size. And then we do the actual copy of A to D, and we do the vector addition, let's say, in a sense. OK, this is recognized as valid at the API level because it is valid. But then when we run JIT compilation and when we will run the dynamic inspection, we will receive this kind of error, where it says that the dynamic testing has failed. In a sense, we're triggering an exception that this is not implemented. So the dynamic sized array declaration are not supported anymore. And this is useful, I think, for programmers to train them, because we are using TornadoVM, where the developers will know how to code things. But it's useful as well for simple programmers who have used to Java APIs to learn how to code with TornadoVM API and do what we saw with Mary in order to actually express the computations and launch them on GPUs. OK, maybe now it's the right time to ask for questions before we go to a break. Yes?
So how does this compare to TensorFlow? Not even performance studies of this compared to TensorFlow?
That's a good question. So how does it compare to TensorFlow and these kind of frameworks? So TensorFlow right now, to support this kind of execution in the Java world, I think it has some wrapper calls for Java functions. What we described here, and Christos focused a little bit earlier, it is that TornadoVM enables the actual JIT compilation. So everything is Java, and is a part of Java is compiled to run on GPUs. As far as I know, I'm not sure if TensorFlow supports. Do you want to take the mic to address the question? Yeah, we have Christos.
So TensorFlow and Onyx and all these runtimes that they do, let's say, machine learning, they are orthogonal to TornadoVM. So, for example, imagine a use case where we have a TensorFlow, we call it through a Java binding, and then we get the result from TensorFlow, and then we want to do something additional on the data, which is not supported by TensorFlow or Onyx. TornadoVM gives the capability to take this data and do all the execution on the GPU. So if you have a code base that already uses platforms like TensorFlow or Onyx, Tornado will not replace them. But if you want to do additional stuff on GPUs, Tornado can complement all those systems. Now, our dream, and this is our dream, okay, it is to make a system like TensorFlow, make a system like PyTorch, make a system like Onyx natively in Java. So we never have to worry about integrating another system into our Java ecosystem. And hopefully this future will come soon. With TornadoVM and Project Babylon, as developers start implementing, we're going to have our own Java world, let's say, ecosystem to compete as a programming language or as a system software. But that being said, I mean, this is my dream, let's say, but in reality, all these are complementary. Ideally, the ideal situation, when it comes to GPU programming, and now I know my answer is very lengthy, the creation of the code run on the GPU, for us, it is a problem that is being solved. We have TornadoVM, we have other LLVM compilers, you can create high-performance code. The problem is data transfers, is how to run on the GPU with moving the data as less as possible between the GPU and the CPU. Because it doesn't matter if you have high-performance computation. If your system doesn't support the developer to persist data on the GPU, so you can just copy them once and then start streaming data on the GPU and consume them on the GPU, all the performance will be lost. The performance will be lost as soon as you start moving data. So if you have Onyx or TensorFlow, and then you want to chain these operations with a native Java, and this is why we went to Project Panama, because having a memory segment, a unified data type that can be off-heap, allows us to pass pointers between different systems and persist the data on the GPU, and also do the compilation and run on the GPU to get the maximum performance out of the whole system. It's not perfect, it's not ideal, it's not beautiful, but as we transition the Java ecosystem in this AI world, it offers capabilities that we can actually implement these kind of things. So to recap, at the moment, it's not a replacement, it's a complementary tool to all the systems. But we hope in the future to be also another, let's say, first-class citizen in this kind of AI computation, which is written natively in Java.
Yes, and I think, there is a second question.
Yeah, I have two questions. One regarding you had like this simplified version of reduce and the other attribute, but also an optimized version that goes into the low-level implementation. And what's the performance difference between those two? Because you said there are performance differences, so I was interested in what the difference is. And secondly, when you build up your test queue, you have to define a grid. And does the grid increase memory size, memory consumption, or how does that relate to VRAM on the GPU?
Okay, great. So I'll start from the second question. So regarding the grid, you just define it. Well, in a sense, it is an object, but this corresponds to the memory size that you have in your JVM. So it's not directly related to the memory that you allocate on the GPU side. So the grid is just used to define the actual work items, the threads that you will run on the GPU. So if you have an array allocated in Java of 120 elements, if you pass a grid of 100 elements, 100 work items, that means that you will have 20 elements that are not being processed. So this is the way to express it in Java, this kind of behavior. So it is not related with the GPU memory. And the first part regarding comparison of the actual optimized version of matrix multiplication with local memory, we have done some performance analysis, and we have seen that by accessing, well, it's not only us. I mean, it's also in the white papers of CUDA and from NVIDIA. I mean, utilizing local memory can help you. Thread tuning can help you. I mean, you can get up to, I think, 10x in performance improvement, pretty much. And we have some results also in our papers that we have published. And yeah, I think the same stands also for the reductions. So we have performance analysis associated in our results. Right now, I don't have the number in my mind, but in a sense, what TornadoVM offers is that the compiler can recognize reduction patterns and can optimize them into a parallel implementation and do a final reduction in the GPU. You get the correct data back, and this is faster than doing that sequentially on the Java world. Yes, another question. That's a great question. Yeah, it's a first part. So from Java bytecodes, we go through the GRAL. So the GRAL IR, it will have an intermediate representation where we're actually lowering the Java, let's say, hardware agnostic part of the graph into a more platform-aware implementations for OpenCL, PTX, and SPIR-V. So in the compiler, in the JIT compiler of TornadoVM, it is an extension of GRAL. So it is written in Java, and we'll have extended classes that optimize the behavior of the code. So we don't have LLVM, we have GRAL, and we lower it to 3 backends. And this is part of the advanced session that will follow after the break. So we will have some, we will show you, Michalis will show you how we use IGV to see the graph, to traverse it, to optimize it through the phases that we have implemented in TornadoVM, in order to be able to actually compile this kind of parallel computations.
How does it compare to, say, NVCC performance versus your optimization?
How it compares to NVCC, the compiler? That's a good question. I don't have the answer, to be honest, how it compares directly. Well, the thing is that NVCC doesn't support Java. So, I mean, it's slightly different. Regarding the computation, you mean?
You can always write the matrix multiplication.
Yeah. Okay. The compilation time.
The produced.
The produced, the performance. Okay, Michalis can address it. Yeah.
Yes. So if I can reply to that, so our performance in comparison pretty much is comparable with the NVCC, because when we generate the PTX code, we directly invoke the NVIDIA compiler. So it's not like we're responsible to generate the machine code. So we get for free all the optimizations that are available in the NVCC. So that's why in main performance studies that we are doing, our OpenCL backend performs very well, because we directly go from OpenCL, we pass it to the NVIDIA, to the NVCC. So the NVCC generates the PTX and SAS from our OpenCL. So our performance is comparable to native code. So if you just code it in PTX or in OpenCL, the performance would be the same, without getting into all the hassle to write it manually.
Any more questions? Yes.
Do you use the truffle framework in your compilation steps, or you just enhance the GRAL compiler to directly work on bytecode? Is your AST based on the truffle?
Well, yes. Well, yes, we extend GRAL, that's for sure. But right now, when we built Tornado, we were not running with truffle. So if we want to combine them, yes, we can combine them with the Truffle framework and build TornadoVM to run with Truffle and be used by the other programming languages runtimes that are implemented on top of Truffle, like R, Ruby, Python, Graal Python, these types.
No, I think my question was more related. So you're not leveraging the Truffle framework for your compilation steps, not for other.
No, we are not using. Yeah, correct. We are not leveraging Truffle for the compilation of Tornado.
It's vanilla Graal compiler for us.
Yes, it's a pure Graal compiler. Great. More questions? Okay, I don't see anything, so I think we can take a break. And we will come back with the advanced session where we will visit codegen, orchestration, and how we have built a Llama 3 implementation running on Java. And we'll have a demo as well.
Hello, everyone, and welcome back. And welcome to the advanced session of TornadoVM. So at this session, we will show you what happens under the hood and how we'll start with the deployment of the functions. So how they're actually deployed into GPU devices. Let's do a very small recap of what we saw before the break. So before the break, we essentially saw how you can program a TornadoVM application with either API, either the loop parallel API or the kernel API. And then Thanos also showed you how you can dispatch the function and the data and eventually launch the computation. So now let's have a closer look of what happens under the hood when we call execute. I will walk you through a bit of theoretical examples about this, and then my colleague Michalis will show you in action how all this works. And essentially, we will explore all this architecture, the software stack right here that you can see, how they connect with each other and how they effectively compile and execute the applications. So the first thing that happens when we invoke execute is that the TornadoVM runtime analyzes the information which has been provided into the task graph. It looks at the parameters we have passed to the task. It looks at the different data transfer models which we have indicated for the arguments. And based on this information, it constructs a data flow graph, which now you can see here we have one task, but if you imagine that we have several and there were dependencies in the data, this data flow graph would depict all these dependencies so that later on the data transfers can be optimized, because I/O is a very expensive operation between GPUs and CPUs. After we have generated this data flow graph, this graph gets translated into TornadoVM bytecodes. There is one bytecode per node of the graph. And these TornadoVM bytecodes, they're not to be confused with the Java bytecodes. These are used internally for us for the orchestration. Here you can see all the bytecodes that we support. They're in level total. And they're split into 5 categories. So you can see we have for the context a begin and an end. We have some bytecodes that specify the location and the allocation. We have for the different data transfers from the CPU to the GPU and back for the transfer device to host. We have some bytecodes regarding the execution to launch or to add a barrier. And also we have some bytecodes regarding the state management. Specifically, we have the on-device, which verifies that an object is present on the device, and the persist, which ensures that an object stays in the device. These are very useful in order to optimize performance and reduce the I/Os. So after we produce these bytecodes for a program from the data flow graph, these bytecodes are passed to the TornadoVM execution engine. And this engine essentially iterates over each of the bytecodes to perform the action that they indicate. So first it goes through each of the alloc bytecodes in order to allocate some buffers on the GPU memory. Then it goes through the transfer host device bytecodes to transfer the data from the CPU to the GPU. And then at some point we reach the launch. So when we do reach the launch is when you actually trigger the TornadoVM JIT compiler. The TornadoVM JIT compiler is built on top of GraalVM. So this means that we essentially take all the optimizations that Graal has to offer. But apart from that, we have extended it with some of our own phases, some common optimizations for the GPU devices. Like you can see here, we have to detect the parallelization, for the reductions, and many more. And then, depending on the vendor, on the backend that you have chosen, we have some specific optimizations per backend, essentially, so that we optimize the best possible kernel for each. And here, I have only put some, but there are many, many actually. Michalis will also show them to you, so you can see how many there are, which I think is a testament to the maturity of our compiler at the moment. Let's go through now the compilation flow to see how it works internally. So first, let's say we have the TornadoVM program, using either API, either the loop parallel or the kernel context. This goes through the Java-C compiler, like any Java program, in order to generate the Java bytecodes. So up to this point, it's regular compilation. There is nothing special about it. From this point on, we jump to the TornadoVM JIT compiler. So we take the Graal IR, we extend it with some common phases among backends, and then depending on the backend that we have chosen to compile for, we generate, essentially, we get a different IR representation, which we optimize with our new phases. And then we get the low-level code, and we dispatch it with appropriate drivers. So, for example, if we get the PTX code, we dispatch it through the CUDA drivers, the OpenCL C code through the OpenCL drivers, and for the SpearView binary, you can either deploy it with level 0 or the OpenCL drivers. And there is also Metal coming soon. So after this execution is completed, we jump back to the TornadoVM execution engine, which traverses the rest of the bytecodes and performs the rest of the computations. It transfers the data back to the CPU, deallocates the memory, and then the computation ends. So now we will pass to Michalis, who will show you in practice how all of this works together.
Thank you. So hello, everyone. And now, what I'm going to do is that I'm going to show you how you can do all these things in practice, because Thanos and Mary explained in detail how you can run a Tornado program, so how you can express what you want to flow to the GPU with the API, how you can dispatch it with the execution plan. But I'm going to show you a bit more advanced techniques of Tornado and how you can really analyze what you are running. And this is going to happen in 3 different pillars, let's say. First, I'm going to show you how to analyze the code generation. So what we saw just now is that you mostly see so far that how you express your parallel workload in Java. But we're going to analyze a bit how the GPU code looks like. But also here, I'm going to show you the intermediate representation. So how a Graal IR augmented with the TornadoVM nodes and phases, how it looks like, and how you can see what kind of effect has the different optimization in the IR level, and possibly how you can express these optimization phases if you have a workload that does something special. Then I'm gonna try to discuss about how you can analyze the orchestration. And Mary just showed us the bytecodes. And bytecodes is a very critical part of TornadoVM to optimize the I/O, which is crucial for the GPU. So I'm gonna show you how you can debug the bytecodes and see if your program does any excessive I/O, like excessive allocations or excessive transfers, or you are copying data that shouldn't be copied. And finally, I'm gonna give you the last hint, which is our profiler. And the profiler is a way to really analyze how the program executes in the hardware level. So our profiler uses the events, the hardware events that each hardware vendor like NVIDIA, AMD, Apple uses. So we profile direct the these events, so you know how your program performs in terms of hardware. Let's start with the code generation then. Before going to the code generation, I just want to give you this disclaimer because we get that question very often. Tornado is just a CLI that we build for our convenience. So Tornado is just a CLI that runs your program and has very simplified commands for all the different things that you want to analyze your program. Doesn't do anything special, like initializing the IntelliJ, printing the kernel, enabling the profiler, calling the IGV for visualizing, nothing fancy. So Tornado, you can just run it as Tornado as Java, pass your options and then your class path and your class, and it just works. So if you want, let's say, to integrate a Tornado application into your project or port it to IntelliJ or to Eclipse or to do something in your own way, you can just directly install Tornado through the installer script, like Thanos showed you before. And once you verify that you have Tornado installed in your system and you run Tornado -- devices and your device appears, and you're settled. Tornado is ready to go. But if you want to run it as pure Java command, just use Tornado -- print Java flags, and you're going to see the options that you're using, your export, your modules, where is everything that Tornado uses. But for the rest of the, let's say, tutorial now, I'm going to just use the Tornado CLI for convenience. OK, so let's go to see some code. So here I have the terminal. I have already built Tornado. Let me try to run. So now I run the same example that you have seen previously. So as the matrix multiplication, so here is Java. In my case, I use Java 21. Yes. And then I pass the options. So in this case, in my system, the Tornado options look like this. This is for an OpenCL backend. The module, the export list, and some runtime classes, and this is it. Now let's switch to the Tornado CLI, and OK, so for the same example, I'm going to use the Tornado CLI. I run the same matrix multiplication that we've seen before. If you want to use a CLI, you can use the Tornado --help. And you can see a number of different options that they can help you analyze your program. So you can see the version. So what is it? The Tornado version. You can see from which commit. I built from master. I have only backend OpenCL installed. But also you can see some other things like the print flags that I showed you before, the devices, and some other things that we're going to get now through them. Let's recap. Now we want to analyze our generated code. Let's see from where we started. So we started from this example that previously Mary and Thanos went over. We have a matrix multiplication that we spawn threads in 2 dimensions. And we know that we spawn threads in 2 dimensions because we have global ID X and global ID Y. And then we have a serial loop that calculates the dot product. And finally, we have a store. And just to revisit what we've seen earlier, if we see what corresponds into OpenCL, it looks like this. So this is a pure OpenCL program that previously you've seen, that performs the matrix multiplication. And you can see that we have get global ID 0, get global ID 1, which is in par with what we see in Tornado. Then we initialize the sum variable to 0, and then we have a serial loop that iterates over width, and it does the dot product. And finally, it stores the dot product into some index of the output array X. Same happens with Tornado. 2-dimensional threads. We initialize sum to 0, a serial loop that calculates the dot product. We store the output of the dot product into C at a specific index. This indexing is like this because we use a 1D array flatten. OK, now we know that if I have an OpenCL program, I'm a GPU programmer, I can get the OpenCL program, I can write it with Tornado, and it's pretty much one-to-one par. But let's try to understand what Tornado does under the hood and how we can analyze it. As we've seen before, okay, we just run it. So let's see. Now we want to see what actually runs on the GPU. So we can do that by going in the Tornado option and say, okay, I want to print the kernel. This means that Tornado internally stores the source file, the .cl file, the .ptx file, or .sprv file in a code cache. So now we instruct TornadoVM to say, okay, before you are passed this CL file, ptx file to the driver to compile it into machine code, print it to me so to understand what's going on. We are printing, and this is how the Tornado OpenCL code looks for the same example. I'm going to open here the OpenCL, the pure OpenCL version, to see. Don't get intimidated by the fact that it's a bit lengthy. It's because the Tornado compiler uses an SSA form, so it's a static signal assignment. So each variable is used once, so nothing fancy. I can tell you that structurally is exactly the same. And let's try to go over it and see how it looks one by one. And again, here we see one thread here, another thread here. It's the same thing like the pure OpenCL. Then we see a serial loop that has two loads from the global memory, two loads from the global memory. And then we start looking and see something different. So here we don't see a multiplication, then, an addition to sum, but we see this FMA. So while even when we initially started coding this, we used let's say this OpenCL example to write in Tornado. If we run through Tornado, we get some optimization for free. And this is all the magic that the TornadoVM compiler does and using Graal does for us. So this special instruction here, the FMA, it says that I can see in your code that you are doing a multiplication addition in 2 steps. I know it's an FMA. There is a hardware unit on GPUs that does FMAs in 1 cycle. So TornadoVM compiler takes the initiative and says, OK, I'm going to optimize this, reduce the number of instructions, and instead of having this split into 2 steps, I'm going to optimize and use an FMA. And then each hardware vendor has a different hardware unit for that. And that's great. So we start from a pure OpenCL program, one-to-one with what you can find online as OpenCL example. You code with Tornado, but then Tornado is going to optimize it for free for you. And the same thing is going to happen for PTX. So let me recompile Tornado. And, let me recompile Tornado. But now I'm going to say make backend equals PTX. So now I'm compiling again Tornado with the PTX backend. So now instead of generating OpenCL code, it's going to generate PTX code. And just another disclaimer, everything runs in this laptop that I have here. So I have a beefy gaming laptop with an RTX 5090, 24 GB of RAM, which is great. So now, as you can see, I rebuilt Tornado with PTX backend. I can verify that it's PTX by running Tornado devices. OK, I can see here that the identifier says that the driver is PTX, so we know that. And let me fire again the same command as a print kernel. And this is PTX code. And through the same iterative process, it works for SPIR-V, and in the future that we're going to release the Metal backend, it's going to do the same. And this is a very good way to inspect what kind of optimization Tornado does in terms of the code that you are generating. But let's step back, and what we've seen here is how our Java code translated to GPU code instead of PTX, OpenCL, SPIR-V, whatever. But there's an intermediate layer, and it's what our compiler does. You asked before if it's based in LLVM. No, our compiler is based in GraalVM. So we have this, let's say, option to examine also in terms of the IR what's happening, how our Java code has been slowly lowering to GPU code through the different transformations. And because of that, in order to do that, we can use the IGV. So in IGV is Ideal Graph Visualizer, is a way to visualize GRAL IR, the GRAL IR. So we're going to go back again to our fancy matrix multiplication example. And now, instead of saying print kernel, I'm going to say IGV. Now, it's going to instruct our compiler to generate the intermediate representation that GRAL IGV uses to visualize the GRAL IR. So now I open the IGV here. And in what I'm really interested here is that I'm going to go here, OpenCL frontend. And this is a very extended list of optimizations. So here you can see about 200 optimization phases that our Tornado codes passes in order to be GPU code. So to remove all the Java-related semantics and keep only what is useful to generate GPU code. As you can see here, there's a mix. So Mary before told you that we use vanilla GRAL. So we take for free optimizations that are like constant folding, partial escape analysis, loop unrolling. We get all that for free from GRAL. And we spend all the extra effort to introduce optimizations that are performance critical for generating code for GPUs. And what we are following so far is this FMA instruction. And I'm going to go just to the point that this FMA optimization happens. So here, as you can see, that there's a phase, OpenCL FMA. We have different PTX FMA, SPIR-V FMA, Metal FMA in the future. I'm going to try to look into the basic blocks. OK, I'm not going to get into specifics what's a basic block right now. But in what I'm interested to look at is that here is the before applying the FMA, and here is after applying the FMA. And by looking the diff into the IGV, here, we are going to see that our optimization so that we have two reads from the global memory that they do multiply and add. And in the next phase, it replaces these two instructions with an FMA. This example might look very, very simplistic for you, but this is the power of TornadoVM that is very easy to apply different optimization for GPUs. So we have another project that has a completely LLM inference in Java, and it's based on this idea. So we do this optimization for quantized types, so to replace a full precision type like FP32 with FP16 that are performance critical for GPU, etc. And you can see here that we do it also for inverse route because division can be a performance bottleneck for GPUs. For atomics replacement, we have partial loop unrollers. So based on the hardware that you have available on the device, we apply a different set of optimizations. So we can prevent the compiler to do optimizations that might, alter the performance, or we can do that. So we dynamically compile the code for the available device that you have, and this is one of the real, performance killers of TornadoVM. And going back here, another thing that you can examine. So now, to recap, we've seen that how the Java is being translated to OpenCL code or PTX, and what's happening in the intermediate layer. And before going to that, I want to show you that optimization. So So this is the exact optimization that we have written in order to do the replacement for FMA. It might look simple, but this FMA replacement can give, let's say, for us a 15% improvement in terms of the GPU code that we're generating. And we have a whole collection of them we have a whole collection of this kind of optimizations. Now that we've seen the code, let me jump back into my slides. Now that we've seen the code, we need to analyze the execution. So in order to analyze the execution, we need to look into the TornadoVM bytecodes. Okay, because we need to understand. Again, I need to state that GPUs are critical for performance for GPUs is the I/O. So we really need to copy to the device and copy out what it's really necessary to do that. And so far, we haven't seen any other way to assess that. In the API level, we have the different options that says transfer from host to device with the two different options like on every execution or just once. But we just need to see how this reflects to our VM and how the TornadoVM really does that. And also, we need to understand the dependencies between tasks to avoid that we do any excessive copies and understanding the memory management on the GPU. So this is basically in terms of allocations and deallocations. And in order to do that, I'm going to go back into the example that we see. And I'm going to run the same thing, and now with a different option. And this option is -- print bytecodes. While it runs, let's revisit the example in the API level. And what we should see in terms of bytecode, it is on the first execution to copy two different matrices. These two matrices are float arrays. Then the execution of the kernel should take place. And then on every execution, we should see a copy out. So this kind of behavior, we have expressed it in the API level, but we run the program, but we need to find a way to verify and to verify that this is actually what's happening. So we have printed the bytecodes, and as we mentioned, this runs for multiple times. And I'm going to go here and see the bytecodes on the first run. So what we see here is that we have 1, 2, 3, 4 alloc bytecodes, and we see that we have allocated 1, 2, 3 float arrays, which is in par with what we have done in the API level. So we copy in 1, 2. We allocate 1, which is empty for the output. So Tornado is not going to do an excess copy-in. It's just going to do a malloc on the GPU side of things. And then we have 1 alloc, which is hidden from the API that just allocs the kernel context API, which is a container object for us to be able to express let's say, the GPU programming API intrinsics in the API side. So, OK, this is in par with what I expect. I have 4 allocations. And then I can see that I have transferred to host to device 1, 2, 3. OK. And I see that there is a status. Status transferred, status transferred, status transferred. So what happened here is that I have allocated. I know that I need to transfer the data to the device to do the computation. And if you remember back in the API level, we stated that this is transfer once. Data is transferred for the first array, for the second, and for the output, which is empty. And then is a launch. So I execute the kernel. This is actually what I was expecting to happen. Okay, and I can verify it with the messages in the bytecodes. And then I can see that I have a transfer device to host always blocking, which means that I copy out the bytecodes. I copy out the result back to the host. And again, this is one-to-one mapping of the behavior of what I encoded in a task graph level with the bytecodes. So if I run it, I get the correct results, I get the correct behavior, I can verify that TornadoVM does what I instructed to do, with some special sauce inside, like our runtime optimized allocations, the allocation, this kind of things. OK. Now that we have verified that the first time that it ran, it did what we instructed to, we need to check the consecutive run. And this is what's very interesting. We see here that the second time that it runs, now the transfer to host device once, the status has changed to present. So it means that the Tornado runtime can verify that the objects that I'm going to do all these computations already on the device. So I don't need to perform another I/O. And the second time around, if this is a clear array, it's going to just allocate it to 0, and then it's going to fire and just do the launch on the next time. So on the second run, you are going to have you're going to spend time only to execute the actual task and copy out the results, because the code is already hot and is already jitted in the code cache. Data is already on the device. So after you've done this first warm-up run, your device is there, the code is jitted, so you just run and copy out, which is a very interesting runtime optimization you got to do for LLMs that I'm going to show you later. And one last step to verify that it's happening, Tornado behaves as expected, is the grid scheduler. So here we see that we have set up a grid scheduler, which tuning up the threads is very performance critical for GPUs when you do it manually, because it can really impact your performance. Here we see that we have created a 2D worker with size of size. In our case, size 512, so I should expect that I have 512 divided into groups of 16 local work items. So the other thing that I want to verify is that I spawn as many threads I have instructed to through the grid scheduler. And this can happen very easily by going here and say -- thread info. And again, I can see that the global work size is size for the 2 dimensions, and 16 local threads per dimension. So now, with the combination of the bytecodes and the thread info, I can validate that what I have expressed in the API level is what is happening on the device. And it's very interesting. Because it hides all this complexity of the OpenCL host program that we've seen before into just some simple API calls. And everything that I'm doing from the terminal is also an option in the API. So you don't really need to be, a terminal warrior to do all this. You can just tune it in the IntelliJ to do this. We have instructions on the website. Now that we have guaranteed that the code that we are generating is correct and the program behaves as expected, we can go to a more fine-grained granularity and start profiling our application. But because we are moving away from the JVM and we are moving to the hardware, in order to get accurate timings, we need to get down to these hardware events. And this event change between NVIDIA, AMD, Apple, whatever. So we have developed our own, let's say, profiling infrastructure that get this timing information directly from the OpenCL events. And yes, this is in order to understand the performance. Again, it's a very simple command when you are running the Tornado CLI. That's why we like it so much, because so you can go back in this our favorite application for today and say tornado -- enable profiler console. So obviously the performance now is going to be impacted. So you cannot, when you run with the profiler without, you should not expect that you're going to get the same behavior. But this is always you have always an overhead with the profiler. So now you can see that for each individual run, I have a different profiling entry. And this reflects, it collects a combination of metrics. So we have some metrics that are related with the JVM side of things, how much time is taking for us and how much time things taken on the device. And it's going to be interesting to analyze these metrics here. So this is an entry for a single run. We can see S0 is the task graph name identifier, as we did before. And then we can see S0, T0 is the task name identifier. You can imagine that if we compose a task graph with multiple tasks, this can be quite longer than that. So we can have multiple different entries. Then we have the Java method name, which is a method that we are floating. Then we have the device ID, which is when you are running Tornado devices, and you might imagine you can have multiple devices, and then the identifier is 00, so it means backend 0, device 0. If you have multiple devices or multiple backends, it's going to reflect into that. And then we have our device. As I mentioned, everything runs in my laptop, which has a very beefy NVIDIA GPU. Next step is the Tornado total task graph time. So this metric is how much Tornado costs for your application. So when you plug in or you try to offload Tornado, if you get this metric, you can also get it from the API level. You know how much Tornado costs in your system. It takes into account data transfers, execution, compilation, dispatch, everything. So this is how Tornado is going to cost in your systems in terms of timing. And then this is break down into multiple different components. So we have the total Graal compile time, which is how much time it takes for Tornado to compile the Java bytecode into the .cl, .ptx, .sprv, into the GPU code, not to machine code. If you want to get how much time is taking to get into machine code, you need to add into this total Graal time the total driver compiler time. So the driver compiler time is how much time it takes for the code that we have generated for the driver to generate the binary. And then we have the TornadoVM bytecode timings, which is how much time it takes from our task graph to generate the bytecodes that we use for orchestration. And then finally, we have the more fine-grained metrics that they are in one-to-one par with what you're going to get if you're timing this event from the host code in the hardware events. And we have the total kernel time, so it's how much it took just to execute the kernel, so executing the kernel, just this method. The sum is the total kernel time, so if you have multiple tasks, it's going to be the summation. Same things for copy out times, copy in on the task graph level. And then this breaks down into timing of individual tasks, and then we can see the metrics like task kernel time. So in this case, because it's from a separate run, we don't have any copy in or copy out times, because we don't copy out the results in this case. Okay, let's step a bit further now, because previously Mary and Thanos gave a very detailed explanation on how the API looks, how we can use Tornado inside to program our first Tornado program, how the bytecodes work, and then we've seen here how we can examine how our program behaves. Code generation, how the bytecode runs, and how the profiler works. But okay, so far we have seen this, our fancy matrix multiplication, but let's build something that is a bit bigger than that. And obviously, to do that, okay, the terminal tools is good, but we found out through the years that we can benefit from some additional things. So we've been using proprietary tools at NVIDIA Insight, JVisual, the IntelliJ built-in profiler to build and analyze Tornado. We have all tools that are generating all these entries of log files. But last year, we built the GPU Llama 3. So GPU Llama 3 is an open source LLM inference engine that can run multiple different models. And it's all written in Java, all written with Tornado. And it can achieve very good performance, which is a very good performance. So the GPU Llama has two different engines, one for CPU that goes through Llama 3, one for GPU that is TornadoVM. It supports GGUF models. It allows you to switch dynamically from CPU and GPU inference, and supports right now Llama 3, Mistral, 5.3, Qwen 2.3, Gemma is almost ready. But what is most interesting about this project is that since last week, we're integrated with LangChain4j as a model provider. So if you go to LangChain4j and you have an application that implements uses any of the chat model or streaming chat model APIs, you can use the GPU Llama 3 as a model provider. So it's gonna, for any of these models, it's gonna use Tornado to run your inference local in your machine. If it's a machine that supports OpenCL, PTX, PV, so it means that even if you have a MacBook and uses a LangChain4j for local development, you can do it through that. And we have a talk on Thursday that we're gonna deep dive just into it, about only the specifics. So now let's switch gears and let's see how this application looks like. So let me switch into a different directory. OK. And now I'm at a different directory, and let me run llama tornado dash OpenCL dash GPU, and then I want to use a model, so I have a selection models in my machine. I'm gonna use the llama 1 billion, and then I'm gonna give you a prompt. Tell me a joke. Sorry. Oops. And then I'm gonna use the NVIDIA NVTop to see what's happening in my GPU. Okay. Now what's happening under the hood? Okay, it was pretty fast. TornadoVM got the inference engine, it compiled to OpenCL code, it copied all the weights of the model onto the device, and these tiny spikes here, they indicate the inference. And it's great. You can get a very good performance just by running in this GPU. But let me show you how it looks like. Because now we did a very big gap, and we went from single tasks into something that looks like this with Tornado. So this here, I don't want to deep dive into the specifics, but this here is what we discussed before, a task graph. This is a Tornado task graph. And all these different tasks, they are the different, let's say, mathematical equations of a transformer model. So we just got the algorithm, and one by one, we ported it into different tasks, grouped together in a task graph, and then we let the TornadoVM to do its magic. And one of the interesting parts is that here, the transfer to device once, so we copy in only the data only once on the device. So it means that if we want to run inference again, the model is there. We just need to clear the context and just run it. So, and in order to do that, we have a warm-up phase. So we use the Tornado with warm-up. So that's why it takes some time on the beginning, because of the beginning, when you start the GPU llama, JIT compiles all the tasks, transfer the weights onto the device for this model, then it's ready for you to do inference. And yes, but let's try, OK. It looks great, but as you can see now, we went a bit away from a single task. So you can imagine that this becomes a bit more complicated to understanding what's happening. And let's see. Now, if I get into this, try to run the inference with something like print kernels. Oops, sorry. Kernel. Yes. So now we are going to see the code generation that we discussed before. But as you can imagine, because this is much more complicated, the kernel now, they don't look like the matrix multiplication. They look like this. So we need to find a way to understand what's happening with Tornado under the hood. So what I'm going to do here is that I'm going to rerun the same application with the profiler option. OK. And now I'm getting all these metrics. So all these tasks that they might look a bit intimidating, now we can capture the performance with the profiler. But again, the output here is very convoluted, so it's very difficult to understand what's happening. That's why we developed some tools around of our needs. And one of these tools is the Pulse. So Pulse is a visualizer for a profiler, but it's not only a visualizer, because when you run Pulse, what's happening is that our profiler generates output, stores output into a JSON file. So here I can say I just run that with the profiler. I want the LLM JSON, which is where I store it. And now that the JSON is imported, you can see that the visualizer got all these metrics and got some valuable, let's say, analysis on this. We have means, geomeans, medians, and for all the different, let's say, granularity, in task graph level granularity, in task graph granularity, and is helping us visualizing the behavior. The first aspect is this. The task time distribution time. So if I open here, I see on the right-hand side, there's a list with task graphs. And because we have done an optimization when we're coding the llama, so we have one different Tornado task graph per layer. So we control the weights per layer, because we follow the same way that the model weights are encoded in the GZUF. And this is happening because when we are loading the model weights, we store them into a big segment just for convenience, and then we chop down this segment into float arrays like what Mary showed you, we can do and create our data types through segments. And here we see all the different task graphs, and then we see their performance. Because all the different task graphs in this case, they do the same thing, they perform the same computation, we see this kind of uniform behavior. We see that almost they are mirroring, and this is what we're expecting to see. So if we had a bug here, it could be easily to spot it. And then we would know that task graph 13 that does the layer 13, it has a weird spike that it doesn't follow the other. So we would know which layer to debug in this application. And then we can zoom in. So here I zoom in this, which is layer 15, and see how the different tasks contribute to the execution time. And then we see how the different tasks, how much time it takes. And this is actually what helps us to do more optimizations. And if we zoom in this task, which is called Fuse FFN W1 W3, and we go back to the source code of it, it's this task here, okay, and we open the task. What we are seeing here is that we used a very advanced, let's say, way to optimize workloads as GPU programmers with Tornado. So this task here that has this big bar in terms of execution time is not just a matrix vector multiplication. Actually, there are two highly optimized matrix vector multiplications, like this one. So each individual matrix vector multiplication utilizes local memory, it has barriers, it stores the intermediate redux to local memory, which is the GPU cache. So we have two of them that we know that they operate on the same data, cascade with each other on different read-only weights. Both of them, they operate on half-float point arrays, which is FP16 for the GPU. And then we have two, let's say, instructions that they are cheap for us. One multiplication and one silo activation, which is an inverse square root. So this tiny kernel here, if you open any of the LLM inference engines that they have GPU backends, like Llama C++, MLX, you would see optimizations like this. But here, what is great is that you can do it in Java. So you're just using the kernel context API of Tornado, and this is it. And the same way we did for because different LLM vendors, they have different architecture. So we have a layer planner, what we call it, that we encode the tasks different way to express the LLM inference. So yes, one more thing. Okay. If you want to learn more, we have a demo on Thursday about this kind of things and how it works in Langsafe4j. And one other aspect is the viz. Okay, so we have this tool that is the Tornado bytecode visualizer, because as you imagine, when we are generating so many tasks, it's very difficult to dig into the results. And we can see it also from here. Sorry, if we print the bytecodes, it's going to look like this. So it's very difficult to understand what's happening. So we developed this tool that we called it Tornado Visualizer, and it consumes the TornadoVM. It consumes the TornadoVM bytecodes. So now I'm going to show you some more simplified examples. A more simplified example of the bytecodes. But this is it. So if you use the Tornado Viz, you can see what's happening in terms of tasks. So here we can see some buffers are allocated, then here deallocating, then here some minor allocations, and then here we can see allocation, then the spike is a copy in, allocation, spike, copy in, allocation, spike, copy in, and then the allocations. So you can imagine you can use the Tornado bytecode visualizer to understand that you don't have any memory spills here, or Tornado did all the allocations and the allocations as expected. So these two tools help us a lot to develop the GPU llama, and we use them to extend it for different LLMs and different models over time. So now I'm going to pass to Christos to sum up the presentation.
Thank you, Michali, for the very interesting demos. And thank you very much all for making it after 3 hours of GPU programming. We have been talking about matrix multiply and LLMs, but of course, originally TornadoVM was developed for general purpose use cases. So if you go to our website, you can actually check all these codes and use cases where you can actually use GPU acceleration, like computer vision, ray tracing, face detection, and machine learning, and data analytics workloads. So we have examples of how to use them and integrate them. We have a roadmap. So we keep the work, we keep improving the system. Our roadmap essentially splits into 2 parts. The first one is how to provide horizontal optimizations in order to get the performance higher and support more platforms across GPU vendors. And of course, now as we are into this AI era, we also try to augment the Java ecosystem with AI-specific optimizations and platform integrations. And the good thing is, because we are a plugin to OpenJDK, because we essentially tap into any OpenJDK distribution, we can benefit from all the nice features that come from OpenJDK, like our Project Babylon, Valhalla, Leiden. We were one of the first adopters of Panama. And as soon as the new features come into production, we will be adopting them to make TornadoVM better and faster. So to summarize, one more time, you can think of this system, TornadoVM, as a nice-to-have add-on to your JVM. You can plug it in to your system and use it if you need it or not. And it will provide you native GPU acceleration of your Java programs. It's AI ready, so we have a lot of code for inference and traditional machine learning algorithms. It's also integrated with LangChain4j since last week as a model provider. More on this on Thursday, on the talk on Thursday. And as we develop and keep improving TornadoVM, we come from, let's say, we're also developers ourselves, and we're trying to, as we create this production-ready system, to augment it with tools, a tooling ecosystem, which will allow everybody to follow the life cycle of these new GPU programs, which are very challenging, from the development to the deployment and to the performance monitoring. Before we close, I would like to thank our sponsors, because at the end of the day, we're a university, so we are funded by EU grants. So we'd like to thank the European Commission and the UKRI, also industry, who has been so generously funding this project and sharing our vision. If you have any use cases, very interesting use cases, or questions, or you'd like to discuss something, just drop us an email or visit our GitHub, and we are very welcoming use cases and try to think of how to improve the system. So the best thing I'm happy to add is your feedback. And before we close, if you have any questions, please let us know. Any questions? Yes, Zoran. Yes.
What are the spikes?
You mean the benchmarks in the what Michalis showed? Yes. Michali.
The first spike on GPU inference is when you copy in the weights. The second spike is what you see a plateau before it gets down, is while it's executing the inference. And because the results are streaming out while they're being calculated. So you're getting out the tokens on the fly. That's a plateau. And when it does, Tornado automatically free the resources. So when the inference is done, Tornado does all the deallocations. That's why you start flat, spikes, then flat, because the Tornado takes care of all the deallocations on the device automatically. Exactly.
Yes, Michalis saw this. So imagine, we have many things happening. The first time you run, everything will build. The task graphs, the bytecodes, you have to JIT the code, create the OpenCL or the PTX, put in the code cache, copy the model, run. That's the first time. The second time, none of this happening. Why? Because you already have the code in the code cache, you already have the model weights in your GPU memory. So if you want to do one run only, yeah, it's faster to do it on the CPU, unless you want to learn a really large model. But if you have, let's say, as normally, let's say we have the engine running and you get a request, TornadoVM will optimize this to as much as it can.
Actually, because we know this need for GPUs, we have extended our API and the execution plan with a call that it's called with warmup. So you can ad hoc call execution plan .warmup. Maybe you can spawn another process of doing something else. So on the background, TornadoVM is going to do JIT compilation and copy your data onto the device. So then when you are back on the main thread, you can just call execute. So we have examples actually, and we didn't have time to show them, that you can do things asynchronously with Tornado. You can spawn Java threads with different, let's say, instances of a Tornado task graph and and hide, let's say, this kind of warm-up into something different that you want to do it in your task. So it's like any other program. Yeah, it's there, and you can do it in the API level. You don't really need it to dig into the specifics.
Yeah, you don't even need to do it on API. You can just run it once and do the warm-up.
But you can do it programmatically.
Yes. I think it was one question from Volker, yeah?
A question on the bytecodes. When you showed the first example with the matrices, you showed that you allocate the matrix, then you, the first time you have this transfer bytecode, you transfer it, and the second time it was already transferred. But you still allocate arrays.
Yes, but there is a status in the alloc. You could see that is the bytecode, and then there is a status. So it says if it executed or it didn't execute it. So the second time, you're not going to reallocate again.
It's like predicate execution,
yes.
The conditional. We create the bytecodes to have it ready as it would be the vanilla. And then if you want to when you optimize and you want to skip some, you do some predication with the status flag to skip them. And Tornado handles this internally.
That's why you see the status. That's why you see the status that says transferred, and then the second time says present. And you can see it also in the allocation and deallocation. So you can see that the dealloc bytecode, but if the TornadoVM detects that the data needs to be reused again, on the dealloc, you're going to see the status that present. So it means that it didn't delay. Otherwise, the status is freed. So it means you see dealloc bytecode with a freed status, and it means that you perform a deallocation.
Yeah.
We have documented this in the documentation. So if you open the documentation, it's
it has pros and cons, whether to elide bytecodes, so not to have them in your execution, or to have them and jump them. So if you don't have them, let's say, you never know whether you have your bytecode generator has a problem and you skip them. So the predication, it allows you also to play very well with the tools, because when you plug into the visualizer all these bytecodes, you can actually see where the bytecodes are and whether they have been conditionally executed or not. So it allows you to understand the shape of your task graph, the execution, and the actual execution itself, which are two different things, at least in our mind. Yeah. Any more questions? Well, thank you very much for your time and for your patience. GPU programming, and please reach out to us, and we'll be around. So yeah, we'll be happy to hear your feedback and ways to improve TornadoVM. Thank you very much.